Our next presentation this morning is entitled Physiological Response of Peanut Varieties to Drought Stress, and Zhang is going to be our presenter.
Okay. Hi everyone, I'm Qiong. I'm a master's student studying in Auburn University, and Dr. Zhang is my major professor, Dr. Chen, Dr. Bachelor, and Dr. Dan are my committee members. My research is about physiological responses of peanut varieties to drought stress. Drought is a major factor that limits peanuts yield, and drought stress is very common due to the unpredictable rainfall in tropic and semi-tropic areas where peanut crops mainly planted. But in fact, more than 65% peanut crops are not irrigated in the United States, which cause over $520 million loss every year. So to develop cultivars with improved adaptation to drought has become a major goal in breeding programs. So which require to understand which physiological characteristics related to drought tolerant. Water use efficiency indicates how efficiently soil water is used for biomass production. It has been considered to be an important drought tolerant characteristic. In water-limited conditions, based on Pasteur's equation, yield is controlled by 3 parameters: water use, harvest index, water use efficiency. So from this graph in the bottom, we can see that peanut plants with higher water use efficiency usually have higher pod yields. So in this experiment, we studied water use efficiency by measuring photosynthesis and analyzing carbon isotope discrimination. And also we studied other parameters that are related to yield, like harvest index, above ground biomass, photosynthesis, and stomatal conductance. Our objectives are to evaluate performance of drought-resistant varieties, and second, to identify physiological traits responsible of drought tolerance. To do this, we planted different varieties in rainout shelters in Dawson, Georgia at USDA National Peanut Lab. The rainout shelters incorporate the sensitive rain sensors to activate the shelter roofs to cover the peanut crops during a rain event, and retract automatically once the rain ends. And also we use Lycor 6400 to measure photosynthesis and stomatal conductance in the experiment. And for the methods and materials, we selected 36 varieties. Some are drought resistant, some are drought moderate, some are drought susceptible varieties. And there were 5 replications. The plot size was 3 feet wide and 6 feet long. And we planted the seeds in May 17, 2019, and we started the drought stress from July 17 to August 22. That is around 40 days under drought condition. We measured photosynthesis and stomatal conductance for 3 times: 2 weeks after drought, 4 weeks after drought, and a 1 week recovery from drought. And in September 19th, we harvested pods and above ground biomass to calculate yield and harvest index. So from the results of yield, we can see that the yield was significant difference between varieties, and we marked the drought tolerant varieties with those red bars and drought susceptible ones with the blue bars. So from this graph, we can see that the drought tolerant varieties showed a higher yield than those drought susceptible ones. And especially line 50 and line 49, they maintained a high productivity under drought. In this experiment, the average yield under drought was around 1,200 kilograms per hectare. That is lower than 2,000 kilograms per hectare showed in other drought studies. That's probably because the drought stress in real fields usually won't be so long and so intense as we controlled in rainout shelters. And we also calculate the harvest index. Harvest index, the ratio of harvested yield versus total amount biomass, including pod weight, equals pod dry weight divided by total dry biomass. So from this graph, we can see that the harvest index was different, significantly different between those varieties, and we can see the drought-tolerant varieties showed a greater harvest index than those susceptible varieties. Like line 50 and line 49, they had a high harvest index. Then we studied the correlation for harvest index with yield, and we find that the Pearson coefficient value is 0.69. That means harvest index is highly correlated with yield. And you can notice that line 50 and line 49, they had high harvest index and also they have high yields. We measured above ground biomass. It's an important component of harvest index. It includes leaves and stems. So from those two graphs, we can see that the above ground biomass might different between genotypes, but there is no correlation between above ground biomass with yield. That's probably because we harvested the above ground biomass after the plant's recovery. So the drought susceptible varieties cut off and the drought resistant varieties didn't show advantages in above ground biomass. So in that case, harvest index seems like a better indicator for yield than above ground biomass in drought study. And photosynthesis and stomatal conductance are both important for yield. So we studied photosynthesis and stomatal conductance for 3 times, 2 weeks after drought, 4 weeks after drought, and 1 week recovery from drought. And we find that there was significant difference between genotypes for those 3 times. And we also find varieties, they had high photosynthesis and high stomatal conductance at the early stage. And they usually maintain a high photosynthesis and high stomatal conductance later. And also the photosynthesis and stomatal conductance in 2 weeks after drought show the best difference between varieties than other types. So from this graph, we can see the line 50 and line 49. They're high yielding cultivars. They had high photosynthesis and high stomatal conductance. The one reason might be they developed deeper roots to access more water to maintain high photosynthesis and high stomatal conductance. And we're going to study that in the future. But some other high yield varieties like Tip High Olay and line 8, they showed low photosynthesis and low stomatal conductance. That's probably because they have high water use efficiency, and we're going to measure water use efficiency by analyzing carbon isotope discrimination in the future. And then we study the correlation for photosynthesis with yield and stomatal conductance with yield for different times. And we find that there was significant difference between those varieties, but surprisingly, we find positive correlation for both photosynthesis with yield and stomatal conductance with yield. That is uncommon to discover in other drought studies. One explanation might be the drought stress in this experiment was completely controlled by under the rainout shelters. So we find we find the photosynthesis and the stomatal conductance in 2 weeks after drought showed the best correlation with yield than other times. So from those two graphs here, and we can see the Pearson correlation for photosynthesis with yield is 0.47. For stomatal conductance with yield in 2 weeks after drought is 0.52. That means photosynthesis and stomatal conductance, they both positively correlated with yield. And you can see the high yield varieties, line 50 and line 49. They had high photosynthesis and high stomatal conductance and also high yields. But some other yield varieties like Qiong and line 8, they didn't show high photosynthesis and high stomatal conductance, but they have high yields. So our conclusions are harvest index is well correlated with yield, making it a better parameter to predict yield than above ground biomass, seen with drought tolerant varieties in drought study. And next, varieties that have higher photosynthesis and higher stomatal conductance usually have higher yields. They probably develop deeper roots to access more water. And next is line 50 and line 49 are tolerant with high photosynthesis and high stomatal conductance. The last one is some high yield varieties don't show high photosynthesis and don't show high stomatal conductance like Qiong and line 8. Do they have high water use efficiency? And we're going to study that in the future. So for acknowledgement, I'd like to thank you for my advisor, Dr. Sands, and I'd like to thank you for all the professors who give us a lot of help, especially for Dr. Chen. And thank you for all my lab members. And thank you for all the sponsors support for these programs. And now I'm going to take some questions that you may have.
All right, thank you for this presentation. And we have 2 questions for you. The first question is from Dr. Soraya Bertioli. Question is this: drought tolerance is an extremely broad concept and totally dependent on the environment where the plants are being evaluated. What kind of drought is your work concentrating on? Terminal drought, intermittent drought, deep water table, etc. How do you think stomatic conductance would affect them?
For the drought stress we were studying is about the midterm drought, because in Alabama there was a drought season during the growing season, like around 2 months after planting date to it will last like 40 days or more than a month. So we basically study like midterm drought. And for stomatal conductance with the drought or the water use efficiency, the relationship you're asking.
Okay. A second question from a different one is, did you include the drought treatment controls into the experiment and data analyses? Did you include the drought treatment controls into the experiment and data analyses?
No, we didn't set any control experiment. We just set 5 replication for all the drought stress treatments.
Okay. All right. Thank you. And that concludes the time we have for your presentation. Thank you very much.
Thank you.